Hello, my name is KR, and today we'll be talking about the very last topics for my mini series on quantum computers. Today we'll be tackling the nature of quantum computation and its basis on quantum gates. Quantum gates can be thought of as rotations in the Bloch sphere. If you have some sort of example right here is a example of the rotation of the Hadamard gate. The Hadamard gate essentially turns this zero ket into the positive or plus ket right here. So here, this would transform it from an up direction to pointing away towards the plus vector right here. It's pointing this way. Okay. Applying a quantum gate changes the angle of a state vector. And so you would see like some very important properties of a quantum gate, such as reversibility. Since quantum gates are reversible, you can think of them as applying the same rotation of no, of a, for example, for this quantum gate. So let's for this example, so if we have a Hadamard gate right here that's in a superposition right now, applying it again, it would rotate around the axis of symmetry and go point back up again to 0. There we go. Now let's go through a list of quantum gates and changes it makes to the on the Bloch sphere. Well, we don't have to just go through all of them, but we can see that every gate right here can be represented as a sort of matrix, and this matrix corresponds to some sort of rotation on the qubits that it is responsible for. For singular qubits, it will correspond to some sort of rotation on the Bloch sphere of 1 qubit. For 2 qubits right here, for C naught, controlled Z, and swap, this would correspond to 2 qubits rotating. And not really 2 qubits rotating, it's more of one, but the presence of the other correlates to the rotation of the other. And same goes to like multiple qubit operators right here. In this third step right here, we went from this first step of promoting the key that we want, this oracle, to this next stage, this third stage, which is doing amplification. The oracle right here mark this key to be the one we want to promote, the desired key, the desired state that we want to be the one at the end. So because it's marked in a different superposition, if we amplify it with these series of gates, we can essentially, oop, there it is, promote it to uh to the state that we want. There we go. So nung kanina, it has same probabilities, but once we complete this amplification right here, boom, the marked um uh qubits right here now becomes 100%. That is a surface level understanding of Grover's algorithm. I won't go much deeper without having to complicate the explanation. But essentially, this algorithm reveals how um how digital quantum computers work essentially. Quantum algorithms inside of quantum computers use a series of rotations to manipulate the qubits in a way that increases the chance of measuring the correct result. So I demonstrated kanina is that given some sort of key, let's say for this one is this combination, we can use a quantum computer such that if ever within in a database, let's say, it has this key, we can use a quantum computer to promote it and give it as an answer. Quantum computers are not really powerful enough to replicate classical computers yet. So it can be um as of right now, they're not in any way to be replaceable in the next 10 years, but we can use them as such to augment classical computers. You can basically think of them as modern day GPUs. GPUs are really, really powerful. And they can help boost our graphics to like very beautiful that 4K um basically no, a very nice output that we use in everyday life. They're very powerful, yes, but it's only for a niche case, which is something related to graphics or anything really related to parallel computing. And we can think of quantum computers being in the same case with our GPUs. For it to be useful, it must interact to a classical computer. It must be in a quantum classical hybrid architecture, where a classical computer helps guide a quantum computer to do all of the tasks it needs. So it does the task prioritization, it help interprets the probability produced by this quantum computer. But in most cases, in not really most cases, but in specific cases, the quantum computer will be able to help the classical computer in the problems that it was meant to be designed for. For example, would be factoring. It will be a linear search through a unsorted database and so forth. And that is the current state of quantum computers within the modern world. I'm KR, and this is my last lecture for this video series.